So this section is titled Building Functions from Functions in your textbook. You can also sometimes call it function composition, which you'll hear me talk about all the time. So if you want to add a second title up here, function composition. And in just like science, when you make composite things, you're adding multiple things together. So that's what we're going to be doing with functions. We're going to be Frankensteining them together, but not as a piecewise function now, as a composite function. Okay, so there's multiple ways we can do this. We can add, subtract, multiply, and divide functions. Here's how it looks like in function notation if I'm asking you to do those things. So to add something, you would take f of x, and I'm going to use red for f of x all day. You would take f of x, whatever that function is, and literally just add the g of x function and simplify as much as possible. Sometimes there's no sort of simplification you can really do. You just pop the two equations next to each other and call it a day. To subtract something in the same way, all you would do is take the f of x function, since that's what's listed first in f minus g, and literally subtract the g of x function. Subtracting each term or distributing the negative and then multiplying, or sorry, not multiplying, adding, just like you would regular numbers. Okay, for multiplying, it kind of makes sense again. You're just going to take whatever the first function is and multiply it by, or stick it right next to in parentheses, the g of x function. So whatever the first function is, multiplied by the second function, and simplify if possible. And then for division, I guess you could probably guess what's happening here. You would just simply divide f, the function f in the numerator, and the function g in the denominator. But because we know some things about denominators, we also need to leave a note for ourselves here that this has to be given g of x does not equal 0. Because we know denominators cannot equal 0. So f of x divided by g of x, and then we just have to make sure that g of x is never going to equal 0. Now what's nice about this is we've been finding domains of functions for a while, and we'll go back over how to do that because it was also kind of a weak point for us, just generally as all of my classes together. But the domain of these functions just means to combine the domains of both of the original functions. So if both of the original functions have all real numbers as their domain, the combination of them is all real numbers. If one of them has a restriction and then you combine it with something else, you have to include that restriction for the new Frankenstein version. Okay, so let's see what this looks like in real life instead of just in math examples. So we have the two functions. F of x is going to be x squared plus 2. And g of x is going to be 2x squared minus 5x minus 3. When we're doing these kinds of functions, even if it doesn't ask you or prompt you like it does in A, you will want to always try to find the domain first because you need to know what kind of function you're dealing with. So both of these functions are what kind of functions? Quadratics. Quadratics are polynomials, and so their domain is all real numbers. So the domain of the red one of f of x is from negative infinity to infinity, and g of x is also from negative infinity to infinity. Now that means, because they're normal, all real numbers, that pretty much all of my combinations of this are going to also be all real numbers, except for division. Division gets weird. Okay, so don't overthink these problems. If we are going to find the following, we'll do f plus g of x. Literally all we're doing. So here we go. We are going to take the f of x function and simply add it to the g of x function. Not a big deal at all. We can do that. We've been adding stuff since kindergarten, maybe earlier. So anywhere you see f of x, you're going to replace with the f of x function. But we defined f of x to be x squared plus 2. And then I'm going to add the g of x function, which is 2x squared minus 5x minus 3. So you see how I've just literally replaced them with the equation itself? Yeah. Okay. Now we simplify if we can. Sometimes we can't do this stuff. Sometimes after we do that, we're done. Can we simplify some stuff here? Yes. Yeah, we've got some x squareds. We can add them together. That's 3x squared. We've got no like terms when it comes to the x's, but then we have some constants, so we can add them together. So we have that f plus g of x is 3x squared minus 5x minus 1. That's it. Its domain is still all real numbers from negative infinity to infinity because it's still a quadratic. And quadratics don't have any domain restrictions. And both of my equations I started with had no domain restrictions, so we're good to go. Does this make sense? Okay, now if we subtract them, it's going to work the exact same way. I highly recommend on subtraction to use parentheses when you plug them in, just because subtraction, if you don't distribute the -1, it turns into the wrong kind of problem. But all we're going to do here is take f of x and subtract g of x. Okay, so when I do that, we have x squared. I already forgot the equation, and I can't see it on my paper. What is it? X squared plus 2. And we're going to subtract all of g of x. This is where I recommend using parentheses, because you want to make sure you actually subtract the whole thing. 2x squared minus 5x minus 3. We do that so that when we distribute this -1, which I'm actually going to do to show my work, we'd have x squared plus 2 minus 2x squared plus 5x plus 3. Right, we distribute the -1, all the signs change. And now we can just combine like terms. We'd end up with -1x squared plus 5x plus 5. That is subtracting. Which one? Okay, this one's also ended up being a quadratic, so its domain has not changed. It's still all real numbers from negative infinity to infinity. Again, because that's what I started with, both f and g have all real numbers as their domain, so you just plop them together. It's still all real numbers. Questions? Great, let's multiply them. Oh, I heard a wait. I'll go back. Okay, so let's start multiplying. So when we multiply, we're just going to take the first function and multiply it by the second function. I like putting all of these things in parentheses when I'm writing it, because then I remember it's an actual multiplication problem, because that's 2 parentheses move next to each other. So again, we just replace those parentheses, or the f of x and g of x, with the equations themselves. X squared plus 2 and 2x squared minus 5x minus 5. Just literally replacing them. Is there something I can simplify or do now?
It's supposed to be -3.
It sure is. Oop. Thank you. -3. Cool. What can we do to simplify this? Distribute. Now we're going to do double distribution. Doesn't technically follow the FOIL acronym because there's more. It's not a binomial times a binomial. But we're going to multiply all of that. X squared times 2x squared, that's 2x to the 4th power. X squared times -5x, that's -5x cubed. X squared times -3, that's -3x squared. And then I switch and I distribute the second term. Double distribution. 2 times 2x squared is 4x squared. 2 times -5x is -10x. And 2 times -3 is -6. Just a double distribution. We finish cleaning this up. We just simplify the things that we can, which means we're looking for like bases and powers, which only occurs right here. Those are the only like terms that I can combine. So f times g of x is 2x to the 4th power minus 5x cubed plus x squared, that's 1 because -3 plus 4 is 1, minus 10x minus 6. So again, it's just kind of how it looks. You just multiply them because it says to multiply. Does anyone remember what kind of function this is? It technically has a name, but we haven't talked about it. It also starts with a Q, but it's not quadratic.
Cubic?
No, close though, because it does kind of sound like that.
Quotation.
Close, no. Quartic. It is a quartic function. Power 4 is quartic.
Oh, yeah.
You have quadratic, cubic, quartic, and after that we don't name them. You don't need to know that. That's not really that important. That was just a fun fact for the day. But this is also a polynomial. Polynomials have a domain of all real numbers, so nothing changed here. It's not a square root. It's not a rational. It's not a logarithm. The domain is all real numbers. Those are the only three that we've learned about so far that will change and not be all real numbers. If we go on to the division example, that's where we're at, right? Yep, okay. So in division, again, it's kind of set up the way you would think. So we would take, I kind of have to like sneak mine down here. F of x is on top, and g of x is your denominator. Now, hopefully your spidey senses are tingling because you're like, all right, g of x is in the denominator. That means it can't be equal to 0. We will probably have to do something weird with the domain for this. But if we go ahead and write the function, we would have f of x on top, which was x squared plus 2, and g of x in the denominator, let me write that 2 again, which was 2x squared minus 5x minus 3. Now there's nothing I can really simplify here because there's no like GCF for all of the terms that then I can divide away. So that's actually as simplified as I'm going to get f divided by g for this problem. However, when I do the domain, I have to remember that that denominator cannot be equal to 0. So we need to figure out what numbers cannot be plugged into that denominator and include that in my domain. Now this is a quadratic in the denominator, so we're going to factor the quadratic. How would I factor this quadratic? 2x and x sets it up. We're looking for factors of 3 that would add to negative 5. Luckily, 3 is prime, so there's only one option, 1 and 3. It's either 1 and 3 here or switching those 1s and 3s. But let's check this one. The outsides would give me 6x, and the insides would give me 1x. Can I make 5? Yeah, I need the big one to be negative and the small one to be positive, so the my numbers end up being positive. Woo, great, we factored. And now we set each factor not equal to 0, because either way, if one of those is 0, the whole thing is 0. That's the zero product property. And we solve for x. X cannot be negative 1/2, and x cannot be 3. Now my domain when I started was all real numbers. However, we know it cannot be negative 1/2, and it cannot be 3. So instead, my domain now is going to be from negative infinity to negative 1/2 with a hole there, from negative 1/2 to 3 with a hole there, and then from 3 to infinity. If you're like, where, how, what? Here's what I did. In my head, I did the number line that we're used to doing with the numbers negative 1/2 and 3 on it. These are empty gaps. They're holes in my graph. And everything else was part of my domain that I used. So that's the intervals that I listed there. From negative infinity to negative 1/2, from negative 1/2 to 3, and from 3 to infinity. But I did that part in my head at first. If you need the number lines, draw the number lines. If you're like, I got it without the number lines, you don't need them anymore. Okay, we're going to do another example together. In this example, we're switching f and g, and we're just doing the interesting ones, which is going to be subtracting and dividing. This time, f is 6 minus x. What type of function is f? Linear. Linear, great. So we know that linear functions have the domain of all real numbers. And what type of function is g? Square root. Now we know there's a restriction for square roots, that the stuff underneath the square root called the radicand has to be greater than or equal to 0. That would mean that we solve quickly this inequality. that we know that x has to be greater than or equal to -2. Therefore, the domain would be greater than or equal to 2, which is bracket 2, comma, parentheses. Which means that when I combine the two functions together, I for sure have this restriction no matter what. Because it's in one of the original functions, it's a part of the combination. Now we might have an additional something going on, but that's for sure it, yes.
Isn't that -2?
It sure is -2. Let me stop losing my negative numbers. Okay, so let's do some combinations. We're going to find the following and then state the domain. So first things first, we're going to subtract. Notice this time, though, what letter comes first? So we need to make sure we actually subtract in that order, because subtraction, the order matters. So we're going to do g of x, and we're going to subtract f of x. And that's easy, because we can just put those functions where they belong. Remember to always put the second one in parentheses, and if you need to remind yourself by putting this in parentheses, maybe that's helpful. So g of x is square root of x plus 2, and we're just going to subtract 6 minus x. Great. Subtracting means we're just going to add the opposite. So I distribute the negative sign. This is -6 positive x. So I have square root of x plus 2, and then behind it, -6 plus x. Is there anything I can simplify there? Can you like move stuff into a square root just willy-nilly? No. So I'm literally done. That's it for this problem. This is g minus f of x. Once you're done simplifying, you're done, and all we have to do is talk about the domain. But the domain of this function, when you combine a linear and a square root, is just going to be taken over by the square root. This domain is also from -2 to infinity, which we found earlier. Because that square root still exists in it, it has the same domain. Does that make sense? Cool. Let's do division. Division's really the only one where something weird might happen because you're creating literally a rational function. But we're just going to take f of x on top, g of x on bottom because it says f divided by g. Okay, we can do that. So f of x goes on top. That's 6 minus x. And g of x goes in the denominator, which is x plus 2. I can't simplify that anymore. So I'm done writing the equation. I found it. I just need to talk about its domain. We already know that the domain, because of the square root part, has to be greater than or equal to -2 all the way to infinity, right? But now that's in the denominator. So what else is added to this restriction? Yeah, this whole thing cannot equal to 0. So we solve for x. Square both sides. Subtract 2. So we're adding to the already existing domain that x just simply cannot be -2. How does that change how I answer the domain question? Because remember, it originally was like this. That's because of the square root. But now, x cannot equal -2.
So now it's a parenthesis.
So now it's a parentheses. Because it ended up in the denominator. Very good. If it's equal to, you use the bracket. If it's not equal to, you use the parentheses. And since now, because it's in the denominator, it cannot equal that, you change that to a parentheses. So there is times where the domain is going to change, but it's not very often, and it's usually with the division because you're creating a rational function instead of just having a polynomial or something like that. Questions, comments, concerns? Okay, great. Let's go to the other side. Here it gets wild. Composite functions. You would have maybe done this in Algebra 2. Does this look familiar at all?
Yeah.
Sort of, maybe? Okay, we've all had a whole summer since then, so I'm going to teach it like you've never seen it before. So composite functions are when you take the range or the output of one function. So we're going to take the output of one function, and we're going to make it be the input of a second function, which is what this little blurb is saying. When the range of one function becomes the domain of a second function, we call that a composite function. So you're going to be basically doing functions twice, taking the first output and shoving it into another function called a composite function. It looks really weird. Please do not call these fog and goff. Ooh, no, that's not how you pronounce these. This is f of g of x. F of g of x. Or g of f of x. That's how you say those. Please don't say fog and goff. Ooh, I hate it. Okay? It's easier to see these, in my opinion, outside of the ones that look like fog and goff. If you have f of g of x. So notice g of x is an input inside the f of x function. Or when I switch that, g of x is on the outside and f of x is the input in the g of x function. So we're going to start with the inside functions because those are the ones that we start with first. We get the output from the inside function and plug it in to the outside function. It's a lot of ins and outs. Let me show you how this works before you're like, what? Because I get it. It's a lot of the same word over and over again. One important thing to notice, if you want to flip back over to the front page, function g in that second example we did, so flip back over to the first page. Function g, which was square root of x plus 2, that's actually a composite function because x plus 2 is a linear function and square root is its own kind of function. So we have a linear function inside a square root function. That's technically a composite function. So we've actually been seeing these for a while, you just didn't know it. And it's very important that you notice the inside functions because the domain of that inside function still affects the outside function even if it disappears. And I'm using the disappears in air quotes because nothing like disappears. In case it simplifies out, okay, in case you square a square root, that square root still affects the function, so it's part of the domain. Okay, first thing we're going to do with function composition, just to make sure we understand how this works, is we're going to play with some numbers before we write equations. So in this example 3, we're going to suppose, not supposed, that's a whole typo, LOL, suppose that f of x is equal to 2x minus 3. That's our first function, that's our f of x. And g of x is equal to x squared plus 2. I want to find f of g of 3. F of g of 3. That's how you would say that. To find f of g of 3, we would do the following. We have f of x on the very outside. Inside f of x, we're going to be plugging in g of x. But inside g of x, we're going to be plugging in the number 3. And you're going to work yourself from the inside out. If it didn't have, don't do this part on your notes, just look. If it didn't have this, what is that blue stuff asking for me to do? Just plug in 3 where? To g of x. Okay, great. That's what we're going to do first. So I'm going to put this back for a second. Erase. I'm going to put it back. So we are going to attack the inside first. That means we're going to leave this f of x there for a second. And we're going to plug a 3 into the g of x function. Okay, so here I am plugging it in. This is 3 squared plus 2. Right, because g of x was x squared plus 2. The x is going to be 3, so now it's 3 squared plus 2. Well, what is 3 squared plus 2? 11. 3 squared is 9. 9 plus 2 is 11. So now I have f of 11. That looks pretty simple to do. Can we plug 11 into f? Yeah, that's something we know how to do. So we're going to be doing 2 times 11 minus 3. And 2 times 11 minus 3 is 19. So f of g of x, sorry, not of x. We plugged in a number. F of g of 3 is equal to 19. Okay, whoa, pause, because y'all are going to try the second example on your own. So what happened? How did we do this? I don't know. Okay, so f of g of 3 means g of 3 is on the inside. And after I get the output from doing g of 3, that becomes the input for f. So plug 3 into g. evaluate, I got 11. Plug 11 into f, evaluate, I got 19. Okay, give that second example on this a shot. I don't know if it's even labeled B. Is it labeled B? Yeah, example B. If y'all could do that one, please. Okay, if I was starting this off, I only did the first couple steps here. We're doing g of f of negative 2. It means g is on the outside, f's on the inside, but on the inside is negative 2. So f of negative 2, I can evaluate f at negative 2. That would be 2 times negative 2 minus 3. Well, 2 times negative 2 is 4. 4 minus 3, that's 1. Wow, that's not right. Negative 7. I just totally added those numbers wrong. Negative 2 times negative 2. What? 2 times negative 2 is negative 4 minus 3 is negative 7. Okay, I know how to math. Now I have a number I can plug into g. And so I take the g of x function, which is x squared plus 2, but that x this time is negative 7. Negative 7 squared is 49. 49 plus 2, 51. That's g of f of negative 2. Questions about this before we do this with total equations instead of numbers? See how it's just function notation multiple times? Yeah. Okay. The other thing that I can ask you to do with function and function composition is to not plug in a number, but to write a new equation. So this time, in example 4, given that f of x is x squared minus 1, and g of x is square root of x, we want to find g of f of x and f of g of x. Now, before we really get started, we first need to know the domain of f and g. Notice it didn't ask you for it, but that's something that we're going to need to do before we start all of these problems. What kind of equation is f? Quadratic, which means its domain is all real numbers from negative infinity to infinity. What kind of function is the g of x? Square root. Square root with nothing fancy going on, which means we know it goes from the origin to infinity. So from 0 to infinity. That's based on the shape. You know, it starts at the origin, goes up. We know the shapes. Okay, we can do this. F of g of x. That means g is on the outside, and f is going to be on the inside. I'm not plugging a number in this time. I'm just going to have to use some algebra skills to simplify the equation. That means I will be plugging in to the equation g of x the entire function x squared minus 1. Right? I just replaced f of x with this equation. But function notation tells me now, okay, anywhere you saw an x in the g function, put that instead. So now this looks like this. Square root of, replace the x with x squared minus 1. Is there any sort of simplifying I can do for that? No. So this is it. This is g of f of x. You can't take the square root of a binomial unless it's like perfectly square. It's a thing. Now we do need to talk about the domain. We've created a new function, which means I have a new restriction. We know that for square roots, that the stuff underneath the square root has to be what? Not just equal to. Greater than or equal to, yeah. Okay, so we can solve for this. Add 1 to both sides. That's x squared greater than or equal to 1. Square root both sides. X is greater than or equal to positive or negative 1. Why positive or negative? Because I did a square root. Okay, now we also have to throw it back a hot second to something you learned in Algebra 2. And I don't know if when you took Algebra 2 they used this trick, because I think it only makes sense in my brain, but it makes sense to me. When you have inequalities for plus and negative numbers, you have to remember on the number line whether this is colored in inside or outside of these two numbers, because it's an inequality. Here's how I remember this. If you misspell greater, you can spell it greater. That's outside. This is an or statement, which means these numbers on my number line would go this direction. On the outside. Greater is outside. Not a real thing. It makes sense in my brain that if you misspell greater, like greater than or equal to, it's or, it's outside. Greater. Now, before we write down this domain, we have to think about the inside function. Which one did I plug inside, F or G? F. What was the original domain of F? All real numbers, right? So there's not an additional restriction given by all real numbers from negative infinity to infinity. So for this example, the inside function does not affect my new outside because the inside function domain was everything. I didn't have an additional restriction. So we would answer the domain for the new g of f of x to be from negative infinity to negative 1 and from 1 to infinity. I drew that red line on top of the number line to show the original domain of f, which was all real numbers. As long as there's overlap in the colors on your number line, that can be included in your final domain. So there's overlap here and overlap here. That's the part I include in my domain of the composite function. Just as a side note before we lose this, the opposite of greater is less than, and if you misspell less than, that's an and statement. That's the one that goes inside. This and this is inside or is outside. So on your homework you will need that. If it's a less than statement, if you misspell it less than, it's inside. It's an and statement as opposed to an or statement. Okay. Before we say we don't understand, let's do one more, and then I'll talk about both of them and compare them because it's going to make sense why we had to do that weird double coloring thing. This time we're finding f of g of x, which means which function's on the outside and which functions do I plug into it. Okay, great. So here's f of g of x. Okay, that means I'm going to take the original f of x function and plug g of x into it. So I'm plugging in square root of x. Fabulous, I can do that. In the f of x function, anywhere where there was an x a second ago, I'm going to put a square root of x in its place. X squared minus 1 has become square root of x squared minus 1. Ooh, but I'm taking a square root and squaring it. What happens? They cancel out. This is going to be just x minus 1. That's f of g of x. Cool, I found it. There's no more simplifying to do. I got it. If I were going to turn to my number line to try to find out the domain of this, this is a linear function, is it not? Which means that its domain goes from negative infinity to infinity. Okay, but remember, we have to include the domain of the inside function. What was the domain of the inside function? The blue one.
X squared?
Well, it's so square root of x. What's the domain of square root of x? 0 to infinity, with a closed circle on 0 all the way to positive infinity. So I have to remember to use the inside domain, even though it disappeared. There is no square root in f of g of x whenever I actually compose them, but it is a part of my domain. Bless you. This domain is from 0 to infinity. I can't forget about the domain of the inside function, even if it disappears. It technically disappeared. I don't see a square root anymore, so it'd be very easy to forget about it. But you have to include the domain of that inside function, even if it disappears.
Like the inside function being at the start?
Inside, like what you plugged in, yes, at the start. So inside was g of x, And g of x's domain when we started, 0 to infinity. So even though in my final answer here, there's no more square root of x, I would have missed it. Like, 'cause I don't see a square root of x there. I know I used it. It's a part of my domain. So what I like to do in these problems is number lines help me a lot. I color in the number line for this one, whatever I see. This is a linear. It's all real numbers. And I color in the domain of the inside function and see where they overlap. And that's the domain of my final answer. Maybe? Okay.